Thanks, Yu-Chen and Abder for organizing this workshop and for this opportunity to speak here in the workshop. So I actually like to talk about some of our recent work on batting, robotic batting. So our focus in the past few years has been on sophisticated robotic maneuvers, such as batting and cutting deformable objects, vegetables, meats, and fruits. So what does a sophisticated robotic maneuver require? Well, you have to be able to understand the mechanics behind as well as the geometry. And then you can do your planning, you plan the steps, manipulation steps. So that's kind of algorithmic. And also you do some kind of optimization, either optimize the energy or you want to minimize the time of manipulation to make it faster, swift and more human-like. And in order to carry this out, on the backbone of that is some control algorithms. You use position, force, hybrid impedance, admittance, all these kind of controls. But then you still need to estimate the state, which means that sometimes you have to rely on computer vision using filtering techniques. So today I like to focus on the batting task. And then as a byproduct, I'm going to look at the motion estimation of free-flying objects, which is a component of that. So this represents the work with my former PhD student, Matthew Gardner, who's currently working at Boston Dynamics, and Xiao Qian, who's graduating pretty soon. So the goal is pretty simple. We want to hit an in-flight object to the target, just like, batting, baseball or tennis, table tennis or tennis ball. So this is the very fast and highly skillful move because the flight usually lasts, half a second, and the robot has to make the planning and the reaction and actually execute the action within that time frame. And it also challenges the sensing and action because of the short time frame. We like it because it also is kind of intersects the impact dynamics and then the aerodynamics and manipulator kinematics, computer vision, state estimation, and also planning. So there are a lot of potential applications, especially to robots in bore spots. So here's the system architecture. So what happens is that, as you see this object on the left of this diagram is flying, and then it's captured by a high-speed camera at a frame rate of 150. And then, so they're sent to these frames of images are taken and sent to image processing. Those features are identified and give it to a state estimator, and then to estimate the current velocity, angular velocity, and position and orientation of the object. And that whole information is going to help, send it to two destinations. One is to dynamically estimate the drag and magnitude effects for us to model aerodynamics, and also for us to anticipate a certain time, ahead where the bat is supposed to meet the robot. So we have to use a little bit of a projectile mechanics there. So what lies in the center here is the impact dynamics, okay? So the arm has to move right away, otherwise there's no time, okay? As soon as the object takes off, the arm has to start moving and trying to anticipate a time, but that is actually changing. So the pose of the arm is dynamically changing, okay? And then it meets the robot, meets the object, okay? And then there is the, through the contact kinematics and impact dynamics, and it generates within, impact usually is 1/10 of a second, generate post-impact velocity and angular velocity, okay? And then the object now is open loop, you have no control after the bat, so the object is supposed to go to the target, okay? That is used as a task constraint. That task constraint is going to be taken back by, we have a 2-degree robotic arm and to do the motion planning, okay? So the robot is constantly calculating and recalculating the pose and going to velocities at the moment of batting, based on the feedback, which is the estimated state of the object during the flight. So because it's half a second, slightly over half a second, you got only like about 70 to 90 frames to deal with. So there's a lot of work on the impact on restitution, from Newton's kinematic restitution to Poisson's kinetic restitution. to strong energetic restitution. And there's also work, graphical work done by Dabu, and also Roos, and the modeling, frictional impact by Cater, and then Mason and his former student Yu-Wan, and then there's LCP modeling, and then there's sequencing of the impact, multiple impacts into sequential events, and then more recently there's some work on multiple impacts, simultaneous impacts, by Strange and Professor Liu's group in Peking University, and myself, my former student. And also there's the impulsive manipulations for sorting, and ping pong playing and batting, and tapping. So, and the modeling of the impact with the environment is also an important part. And that has been looked at as well, done by Professor Zen, and Ohio University, and then there's Bo Pankosla and Ian Walker. So, and recently there has been some work on catching in-flight objects, and the most known work is Professor Billard, who's going to be a speaker later in a workshop today, of catching, very impressive catching objects by moving the one upon the impact of the hand with the object, and just basically move back, follow the trajectory to reduce the impact and for the catching. They didn't model the impact, but it's dynamic manipulation. And then there's a table tennis robots, the first tennis robot by Anderson. And the most impressive one is actually designed by a group of researchers in Zhejiang University, led by Professor Xiong, whose robots can actually rally over 170 strokes. All right, so now let's get to the technical side. So what is the impact? We're looking at it, 2D impact. One is the bat, the other is the object, okay? So the equation can be, the central equation can be written very succinctly. And so you have the contact velocity, and then this is the inverse inertial matrix, okay? And then that's the impulse. Once you get the impulse, you get everything, basically, because the impulse, and you get the velocities of the object and the bat, and you get the contact velocity as well. So let's say if we get the impulse in the end, okay, but the impact happens within a split of a second, right? It's usually 1/10 of a second. And then you will be able to plug into, Newton's equation and Euler's equation to get the post-impact velocity and angular velocity of the object, which is, in our case, is subject to the constraint of taking the object to the target. So the central question is how to determine the total impulse. So we have, this is the relationship here. We have the impulse, which through the Newton's law decides the contact velocity, okay? And then contact velocity via Coulomb's law will characterize the friction mode, which will affect the impact. And it also dictates when the compression phase ends. And in the meantime, though, at the contact, there's potential energy accumulating in the first phase. That's during the rest of compression, and then released afterwards, after the contact velocity becomes 0. So there's the relationship between the impulse and the energy, because we're using energetic restitution. So we have to be able to track that. Okay, so what we did is basically, we project this impulse along the normal direction and then the tangent direction. The same way we'll project the contact velocity. So there's a case-by-case analysis. This is the work that has been, similar work has been done, back about 20 years ago by Man Mason and Yu-Wan, but they were using kinematic and restitution, kinetic restitution, Poisson's. And we're giving a more compact solution to this. So there are special values for the impulse. So impulse, the normal impulse is the only variable. All the other ones, the tangential impulse, the contact velocity, the energy, potential energy, all of these are functions of this variable. So there are several moments that are critical. One is the end of the compression, that we have a value of this normal impulse. And then the other one is when the tangential velocity becomes 0. And then there's the one, third one is the end of restitution, because we're using energetic restitution. So we kind of attract the energy, okay? And then you look at track the contact modes as well, and that is under the Coulomb friction, okay? So there's 3 kinds of modes. One is a stick, and then the other one is slip, and then there's a reverse slip, okay? So here it basically will give you an idea. And if you imagine this pad as this ellipsoidal object, and then the object is this pentagon, and then so by adjusting the coefficient of friction, contact friction, and also changing the other parameters slightly, we can generate all possible scenarios. These 5 are all the possible scenarios. The first scenario is that the contact slips throughout the impact, okay? And you see this is the impulse here, and on the right, this is the contact velocity. So they are all linear, straight line. So the other one is when the slip contact mode changes into steep contact mode, okay? So this hollow dots here represent where the contact velocity becomes 0. If you focus on this black curve, okay, so that's where it goes to 0. After 0, it stays at 0, okay? But that happens before the compression phase ends, okay? So there's another situation that happens for the slip transition into stick, but it's during the restitution phase. So it's after compression ends. Okay, and then you can also prove that the other mode, if it after slip, the velocity becomes 0. So if it does not stick, then it has to slip, but the slip will have to happen in the reverse direction. So that's the reverse slip. Either happens during compression here or in the last scenario during the restitution. Okay, so impact has been studied by a lot of researchers. And one thing seems to have been neglected in the past is, okay, so you're using Coulomb's law of friction, to model tangential impulse and contact. And then you're using either, kinetic, kinematic, or energetic restitution. Are these laws, fundamentally consistent with each other, okay? Which means that, is the impact of the termination of the impact guaranteed or not, okay? So we like to ask these questions. Will the contact velocity always increase to 0? Because, in the very beginning of the impact, it's actually along the inward normal direction, right? So after it gets to 0, will the potential energy will decrease to 0 to end the impact? That's another thing we have to worry about, okay? So for 2D impact, it is easy actually, using some proof, and you can show that this normal contact velocity will eventually be increasing at a constant rate. And builds on that, we can show that the impact process will end. Okay, so Coulomb's friction and this energetic restitution law, they are consistent, right? All right, so that's what happens within that, a tenth of a second of the impact, right? But after the impact, the object takes off, okay? And it's supposed to go to the target. Okay, so that is the open loop. We have no control. So we like to understand the mechanics behind it, okay? So when the object is flying though, it's subject to 2 forces in this case. One is the drag force, which acts in opposite to instantaneous velocity, okay? So this is typically modeled empirically using this drag coefficient, and then, scaled by the cross, the area of the normal cross section, okay, which is normal to the velocity. And then it's quadratic in terms of the current instantaneous velocity. And then the other one is due to the friction between the air and the surface of the object, okay? And so the air is actually moving with the object, which actually creates different speed of the air and different sides of the object. So when you throw a ball, if it's backspin and it's gonna flow further, fly further, if you use a top spin and it's gonna land earlier than expected, or another example is from soccer. You can do the banana kick, make it bends outward or bends inward, depending on which part of your foot touches the ball. Okay, so that Magnus force is always orthogonal to the velocity, okay, and in the planar cases also orthogonal to the z direction, okay, which is the outward, okay, so direction. All right, so after you have these forces now, of course, you have the dynamic equation. So you get this Newton's law, and that's the differential equation. But this differential equation, if you numerically solve it, then you're kind of doomed, because for planning, you would have to, adjust the bat positions and the, the robotic arm positions multiple times, which means that you have to do planning many, many times. But this numerical solution is too too slow. Okay, so the simulation cannot be done in real time of half a second. So what we actually did is we're looking for a closed form solution. So we basically replace this right-hand side, the velocities with the closed form of velocities under gravity only. So we're ignoring, the air forces, aerodynamic forces. Just use a simple form on the right-hand side. On the left-hand side, we let it be. So we actually are able to get a closed form solution to this ODE. And then we did some verification here using 3 objects. One is a ping pong ball, the other one is a dumbbell. Okay, and the third one is just the block. If you look at this first flight diagram here that has 3 trajectories, the real trajectory is this dashed black trajectory. It happens within a 0.6 of a second. If you don't model aerodynamic forces, and then the red trajectory is where the ping pong ball is going to, okay, which is going to be way off the real trajectory. That means if you're using this for your planner, okay, and then it's going to be misled. And if you use our approximation, then you get the screen trajectory, which stays very close to the real trajectory. We also did the experiment with the dumbbell object and then this block here. And then in all these cases, it turns out that the approximate solution is very, very close. The trajectory is very close to the real trajectory. Okay, so that seems good. And of course, and the object is flying towards the bat and then the robotic arm, you have to constantly do the state estimation in order to adjust the arm and set the right velocity, joint velocity at the time it meets the object, to program the impact. So, so we use this flight estimation. We do 2 kinds. We're kind of mixed EKF, extended common filter, with the least square fitting, and we find out. So one is used to estimate position and velocity. The other one is used to estimate orientation and angular velocity. So here's just a simple illustration here. This red horizontal line is the estimate if you just use EKF on the angular velocity. Okay, and so it really doesn't change. And if we use these squares, okay, fitting, we actually get pretty close, to the real trajectories, and as the object keeps flying further. Okay, and then so this one shows the fitting results over 45 frames and 86 frames. So the A is the real one. Okay, A is actually the modeled one, and then the real one is right here. It's taken by the image. It's the frame, that particular frame, and then that is very close. So in this case, the batting I think happened at around 90 frames. So when the estimate is good enough. So now we have to program the robotic arm. So what's the arm pose? As we know, though, if you pick the contact point for where the impact happens, basically the joint angles are uniquely determined. Okay, so the arm we're using is the 4 degrees of freedom WAM arm. We're basically using the joint 2 and joint 4 because it has only these 2 degrees of freedom that in the same plane. Okay, these are used for batting. All right. And in the meantime, this WAM arm has constraints over the joint angles, velocities, and accelerations. Okay, so we get the angles and we check whether they're in the range, right? Okay, but that contact point is not predetermined. So for instance, if you fix the moment of the flight during the flight of the object, and then the contact point on this dome-shaped object is going to be, around the circle here, right? So you have a one-dimensional set of contact point, which is going to give you a one-dimensional set of poses. Okay? So that is good because we don't want a unique pose. All right, so now impact planning now, we describe the state of the arm at the time of batting using 4 variables, the 2 joint angles and 2 joint velocities. And then there are a host of constraints, there are a total of 16 of them. Only 2 of them are equality constraints. One is a path constraints. After the impact, the object is going to fly to the target. The other one is a contact constraints. These 2 equality constraints reduces the state variables to 2, okay? And then all the other ones are kind of like inequality constraints we can deal with. These are very, by checking whether it's within the interval or maybe convert the condition into a first order logic formula and then use root finding to check the truth of it. All right, So planning now comes, okay, we divide that flighting time of slightly over half second into cycles. Okay? So every frame represents a cycle. So a cycle starts when a new image frame is taken. At this moment, though, the robot arm is still following the old trajectory. Okay? But now with the new image taken and image processing and the feature extraction and do the state estimation and then the planning. Okay, now, at the time of impact, the velocity, joint velocity and joint angles the robot is supposed to achieve now has changed. So now there's a new trajectory. And so here that is about 3 milliseconds. And then the new trajectory takes effect, okay? And it'll last into the next cycle, okay? Even after the next image is taken. So the robot basically constantly modify its trajectory. So here we'll just give you an idea how this happens, at the very initial frames. And, so these estimates, so these estimates V1 and omega 2 represents, at the moment of batting, supposed batting moment, and then joint angle and joint one and angular velocity of the second joint. Okay, so and later on, and they are more and more concentrated, so that which means that it seems like they have reached a consensus. So the camera we use, this is hardware, it's a Ximea high-speed camera that can take up to 1,000 frames, even though you get only very small image frames that way if you wanted to do it, because our flight is in the plane, okay? And so we are able to use this image grade and, just to calibrate it and get very, very accurate result, okay? So we want this object to fly in a vertical plane. That's why we use a launcher, catapult. And these three objects, we did measure their drag coefficients and Magnus coefficients and coefficient restitution and contact friction. All these are measured. So now let's look at some video. So we did 4 sets of experiments. So here's a hanging board, okay? And then every time we just do one batting, if it hits the board, it's regarded as a success. The next one is just basically bat this dumbbell object to, to knock down these toy bowling pins that are in a row situation. And you see here's the miss, actually. The success rate for this is not really that high. This is a very, very skillful task. So what happens here, this video is made by Matthew that shows you, the object starts flying, towards the robotic arm and the planning is going on and you see the trajectory adjustment, the anticipated trajectory pre and post impact trajectories are adjusted until in the last few milliseconds, and then it does not very much, and then it's supposed to go to the target. Okay, so in a third one is to bat this block into the net. And Xiao Qian is actually throwing, so she has practiced a lot just to make sure that it's thrown within the vertical plane. But of course, there are some errors. So it's nice to see that some of these successes despite the errors. Okay? This is all taken in one shot. I just bat into the nets. Okay, and then it starts having misses. But this is actually easy because the aerodynamics modeling is more accurate for spherical objects. Okay. So this is another one. I think this is the last one. It's the 5th one. So bat the ping pong ball to hit it towards, the center point of these concentric circles. As the closer it hits the location is to the concentric circle, the better the accuracy, right? Now it's using a different pose for the robot to do the batting, okay? And this one is actually very close, okay? So now, this is the superposed snapshots will show you basically what happened, help visualize, the second batting task of knocking down bowling pins. All right, so we did some measurements here, and these green dots represent the successes. These hollow dots represents the failures, basically when it hits the board and it's a success, okay? When it's off the board and it's a failure. So this is very good because we're batting a ping pong ball and then the aerodynamics is good enough, 50% of success. For the bowling ball, and you see that success rate is actually not that high, it's pretty low. We did 182 throws and then there are only 50% success. For this particular set though, there are 20 of them, we have 5 success, so this is the one of the higher, one of the groups with higher success rate, okay? In order, we actually also did the comparison with Xiao Qian standing here trying to bat that herself without training. Okay? So her successes are marked here. And you see that this is the difference between a robot and human. Actually, as Xiao Qian is batting more and more, she was getting better. So her success rate was actually improving, you know, and then so the, but despite that, because she had received no training at all before the task, and in this set, her success rate is slightly lower than the robot. Okay, and for this one, I'm just to skim through this. It's about 20%. This is also a tough one because just like the dumbbell, and then the you know, a lot of the failures for the dumbbell is because the dumbbell didn't, the flight of the dumbbell does not stay planar. It just fly off the plane, and then the robot will have no way of getting, sometimes even knocking the dumbbell. So in this case, it's still, even though we're using a launcher, it's better, the situation is better, but because, you know, this is not a spherical object, we had a success rate of 20%. So here we did a comparison between the last group. We did a comparison between the robot and Xiao Qian. So the robot was able to succeed, you know, 25 out of 37 instances, and Xiao Qian was able to succeed, you know, half that rate. And you also see the difference between robot batting. This red crosses basically has no bias towards the, you know, in terms of directions, whether left-hand side or right-hand side. Whereas Xiao Qian seemed to be a little bit right-handed because all of her hitting positions are kind of slightly to the right of the center of the circle. Okay. So that's the batting thing. After that, we wanted to move on to 3D batting, and then Matthew noticed that, okay, but first of all, how are we going to deal with this motion estimation of the flying objects? We realized that this can be a problem for itself. So Matthew spent the last 3 years of his PhD working on this problem. So he was never able to come back to 3D batting. And so this has a lot of applications. There's a spacecraft, you know, attitude estimation and tracking debris and asteroids. And, you know, for catching and batting, you know, you have, like we just show, and also for human training in sports, and virtual reality and underwater explorations are potential applications as well. So here's a diagram for this task. Basically, we have, you know, the observables are the features of the object during the flight. And then we have to set up this dynamic system using aerodynamics. Now it's 3D, and then using a common filtering, okay? And then we do the pose and motion estimates. But these features, you know, we use 2 cameras. These features, they only appear in a number of frames and they disappear. So we have to track these features. We use a planar graph to do the feature tracking, you know, and have, you know, every hypothesis will set up a correspondence between the feature and then the image points. Okay, so there's a lot of related work from, you know, velocity estimation, vision-based, and kinematics-based using accelerometers, magnetometers, and also the aerodynamics, pure aerodynamics. As that's the route we're actually going to follow in terms of modeling dynamics, and common filtering from the initial work by Common, and then there's also the extended Gaussian common filter, Smith, and then there's the unscented common filter, and, you know, all these and done by people from filtering and control, and also from vision. And then there's also the VINs recently, mostly for mobile robots, and the constrained common filtering, and more recently the IEKF, the invariant EKF, which basically tracks the state in the using the algebra. Okay, so the NE groups, basically the transformation groups, which automatically satisfy the constraints, such as, you know, unit quaternion to represent orientations. Okay, so then there's some work from computer science side for the planar graph matching. So what happens here is that, during the flight, the object has a velocity and angular velocity all in the body frame. So it's subject to the drag forces, which is typically modeled using empirically. And then there's also subject to the Magnus effect. Okay, that we have empirical formula for that. But in the meantime, though, because of the velocity, it generates velocity potentials. You would have to solve the Laplace equation to get that. And then from the gradient of that, you get an air velocity. Okay, and so they plug into the Bernoulli's equation to generate the air pressure, and you integrate over the surface to get, the lift forces and then also the torque. Okay, and you combine lift force with the drag force, you get, force and torque, on the object, and then you apply, that to the Newton's and Euler's equation, so that to close the loop. All right. So what are the observables? So we have two cameras right here, FC and FC prime. So you have these feature points here, for instance, like a vertex of this polyhedron object. And then it's in the body frame, converted to the world frame, and then the camera frame, and then perspective projection, and then the torsion, distorted the image, and finally get the image point. Okay, so that will conclude the loop. So the system observables are, the images of the point features, and also we use the, because of these two cameras in the epipolar position configuration, so we use the normal epipolar planes for these features. We get, 27 variables, including, center of mass and object orientation by a quaternion. We also have camera orientations, because the camera orientation is not exactly known, even though they are known to a good approximity. And then we have the velocity, angular velocity. We also have the camera's focal points. So, okay, and then you combine these camera dynamics and the object flight dynamics with camera projection, okay, and then so you get this dynamic system, and you have the observables. So now it's subject to 3 quadratic constraints on the quaternions, because these quaternions have to be unit quaternions. So what we're doing here is to use common filter to minimize the posterior covariance, and we exert these constraints using Lagrange multipliers, make sure that the state, stay in the SC3, basically, okay? So this is kind of like equivalent to the IECAF, invariant ECAF. We get the common gain, all right? So now, one big hurdle here, obstacle, is to track the features, okay? So let's say we have the model of the object, which is this polyhedral, which can be represented by this planar graph that captures topological structure of the object. Okay, every time though, the image is only viewing a partial object. So we set up from this feature extraction, we set up an image graph, and then we have to hypothesize the correspondences between these vertices in the image graph and those vertices on the planar graph, which are essentially the vertices on the polyhedron. Okay? So we basically maintain multiple hypotheses. For every hypothesis, we just give it a common filter, and then we kind of evaluate these common filters, let them compete, and then delete those that are inadequate, and also generate new ones. So by doing this, we're able to do the tracking. So we did some verification here, and one of them is to use the wooden frame and using accelerometers as independent validation. And the second one is to use the Rugby Ball and flowing, and this is aerodynamics. We use the quadratic constraint common filters with aerodynamics modeled, okay? And then as you wonder whether aerodynamics really helps, okay, we did measure using the reprojection error to compare 2 versions of common filters with or without aerodynamics. As you see, the errors with aerodynamics is consistently, here represented by this black curve, okay, consistently below that used without modeling aerodynamics. Okay, that's for the first camera and the second one as well. So now here's where we use this feature tracking for this polyhedral objects. And then on the right-hand side, these are the snapshots taken simultaneously by the cameras. And you see that here on the bottom right, you have this hypothesis generated, lasted for a while until both are killed. Because every time, when one vertex, some occlusion happens, vertex disappear or appear, and then the algorithm would have some difficulty tracking the features, and sometimes you would have to regenerate hypotheses, which is not really a problem because this new generated hypothesis number 3 here and the lower end, bottom right, is able to track this very well. Okay, so as I'm running a little bit off, I'm running close to time. Okay, I'd like to just mention some of the future work, which is supposed to be future work for Matthew, but he has graduated. He's now happy with Boston Dynamics, so it's all behind his mind. So we like to do this 3D impact modeling more efficiently. I had some work with my former student, Fei, who's working at Disney right now. And on 3D impact, we're able to compute these things and do the validations, okay? But efficiency is is a headache. And if it's not efficient, you cannot do the planning, because as you see, there's multiple plannings have to be carried out, for every frame there's multiple plannings, and you got, 70 frames. Another thing is about the Super Bowl, phenomenon of modeling tangential compliance. So the tangential impulse is not all dissipation. Some of it actually can store part of the potential energy generated during the impact. And also the trajectories, it would be nice to actually have general trajectories, non-vertical trajectories, just like the banana kick trajectories, for the soccer ball. And we like to do all this in real-time estimation. This is going to be very challenging because, as you see, time is very short. It's only slightly over half a second. I'd like to end this with an acknowledgement. And I think I still have some time in case people are interested in asking questions.
Thank you, Yanbin, for your great presentation. I learned more details of your impressive frictional impact dynamics model now. Are there any questions? If not, maybe may I ask a question, Yanbin?
Sure.
Yes. So basically, in the paper, I think we covered the case that when the inertia between the robot and object is drastically different, whereas in practice, that this assumption might not be always true. For instance, in these box grabbing examples or more common impact tasks, the inertia, the object inertia is kind of not negligible compared to the robots. So in that case, how can we, what kind of robot inertia should we use? How do we compute it?
Yeah, that's a very good question. It's actually, it's a deep question. So here, you're getting into the technical details here. We're kind of regarding the object, mass is negligible. It has mass, but it's negligible relative to the robot mass, which is regarded as infinite. And I think there have been some work like by Khatib's group on this, modeling this robotic arm, the inertia during impact. I think, but they are using Newton's kinematic restitution law for the modeling. So maybe we could plug in that, or maybe use that, and then try to see how to fit in this energetic restitution model.
Okay, thank you very much for the answer.